Hamish, take it away.
Okay, cool. Let me just. Can you see
Yes.
Okay, cool. Let me just go back on the slides a little bit because let's start from here. So yes, this is just something I put together just to help the conversation a little bit. And yeah, we're going to talk a little bit about traffic systems in Burnout and why they were kind of engineered the way they were. I just wanted to kind of quickly go, hey, who am I? I was the primary gameplay programmer on virtually all the Burnouts. I became a producer for Burnout Paradise, but I was still heavily involved in a lot of the technical stuff for that game. And I wrote the traffic system for these games. So I've thought about these problems a lot, and I'm not suggesting necessarily that you copy what I did, but I think it might be useful for you to see some of the decisions that got made and why they got made, and hopefully, yeah, it will be useful. So just to remind people what I'm talking about here, like what kind of traffic system we're talking about. Let me mute that. So obviously, Burnout's a fast-paced arcade racer, and one of the big things, obviously, is weaving in and out traffic, crashing, all those things. This is actually Burnout 2, and we have quite lots of elevation in the tracks. We have quite high density of traffic often. And I know the resolution is not super cool here, but I think you can see traffic going up and down hills, following roads, making turns, all those things. Like the elevation changes are quite big. And we also had quite a range of traffic sizes. So we had everything from articulated trucks to little town cars and everything in between. So we weren't dealing with something that was like everything was uniform and everything was the same. And, it was a fully 3D experience. And it was also Burnout 2 wasn't online, but Burnout 3 was fully online, and we can talk a little bit about that too. And the reason why I wanted to show this track was just like, yeah, we've it's not as simple as just like doing it in 2D. You have to worry about how it all works in 3D as well. We could talk a little bit about why that's interesting. So let's get to the first problem. Splines. They're actually quite nasty to work with. And in particular, one of the key issues is that if you move along a spline at equal parameter increments, if you've got a curve of something of t, equal t increments don't equal equally spaced arc lengths along the line. And so you've got this decision to make about how you want to deal with the spline data. Do you want fixed arc length increments, which is how you would animate something smoothly along the spline, but calculating that is inverted commas expensive, and we'll get to that in a little bit. Or do you want to move along a spline at equal t increments, but of course it'll slow down at the corners and speed up. As you can see, the green dots are equally spaced, but the red dots kind of get denser at the corners, and then they spread out, and they're not evenly spaced by any stretch of the imagination. So that's what happens when you increment t equally across these things. And there's a fundamental decision about how you want to deal with that when you're dealing with anything that's moving along the spline. And naively, you might go, well, okay, I want to place a vehicle or something at the spline point with equal arc length increments so that it moves smoothly with velocity. But I think hopefully I can convince you that that isn't the only option. Okay, so what have we got as a bunch of traffic requirements? Well, there's a whole bunch of things you might want your traffic to do. You have junctions, you might want to stop at certain points, you might want to give away to things, you want them to change lanes, you may want to like cross lanes and kind of navigate space in a whole bunch of different ways. And so we can't kind of ignore the fact that we want to do these things. That's kind of a baked in part of the issue that we need to deal with. And we have to detect these issues in sensible ways. So the first thing to realize is obviously mostly traffic occurs in what is considered a lane. And what's a lane? A lane is basically a linear sequence, a queue of vehicles. And every vehicle has to stop a sensible distance behind the car in front. Generally, you only have one car in front of you. And wherever the parameter is that you're testing, um, the vehicle isn't a singular point, right? It's got length, and you don't want to stop like a fixed distance behind another spline parameter, because if you've got an articulated truck in front of you versus a little mini, you want to stop an appropriate distance relative to those things. So the black dotted lines here are just like, the front and back distance of the vehicle, and obviously you want to stop. The green line and the red line need to touch so that the vehicle behind stops before it hits the back of the car in front of you, right? Unless you want to allow that, but in general, you don't want that to be the case. And so you have to take into account the length of the vehicle ahead and how much space you have of your vehicle. And so you kind of have to track 3 points. You have to track the front of the car, the back of the car, and then some arbitrary spline point, which represents where your car is. And actually, in Burnout, we actually picked the green line to be the actual point on the spline. So the green line is like some meter, a meter or so ahead of the front of the vehicle. And the reason why that's good is because it basically lets you stop that green line at, say, a stop line or a stoplight or a traffic light or a stop line. And you always guarantee the vehicle will be behind it. Doesn't matter how big the vehicle is, if it's an articulated truck, if it's a mini, whatever. If the green line is actually where the spline point is, you will always stop behind whatever it is that you want to stop for. And this has got a lot of advantages. It does mean your spline point isn't representing the matrix of the vehicle, but we'll get to that. But that's the main reason why you want to do it, because it makes all that kind of stopping for things a lot easier to manage. And so here's the advantage: like picking that point ahead means that we kind of embrace the position inaccuracy. So when we said before that the assumption that equal t increments aren't the same as the arc length increments, we just make the assumption that they are. So the reason why we can do this is because the spline density is high enough that this error between the red markers and the green markers never gets big enough for the vehicle to actually overtake, the front of the vehicle to ever overtake the spline point ahead of it. So that green line will always be ahead of the front of the vehicle, which means the vehicle will always be behind it, which means we can always stop for things. And so if we always guarantee that, so we never overlap vehicles when stopping, even though you have inaccuracy, you have a smoothness issue, right? Like your vehicle will kind of slow down and speed up as it goes across the spline. But what we just did was just move the vehicle towards the spline at a fixed velocity. So it wasn't like held onto a spline like at a fixed distance. The car would go at a fixed velocity and the spline would kind of speed up ahead of it and then slow down. And as long as the vehicle always moved towards it at a fixed velocity, then you're always correctly behind it, and you were never more than kind of an area away from it. And this unlocks a huge advantage, which is we could actually update the spline point without calculating anything to do with the vehicle, its matrix, or anything, because the stopping point was always done in parameter space. So we always stopped at like a fixed distance, inverted commas, behind the vehicle, behind its own parameter, because we made this assumption that equal t increments are the same as equal arc length increments. And the way that we could do that was we guaranteed that the spline control point density was high enough that error never got big enough. And this means that you can have a huge performance win. It means that you basically can update the whole traffic system by only updating one parameter per vehicle, and that's just its spline parameter. That essentially the stopping point, the point in front of it. And this can be coordinated across a huge world. It doesn't depend on who sees which vehicle or being in proximity to them. And so you only need to actually turn that spline point into a real matrix when you're looking at the vehicle when the vehicle's in range of being drawn. And so the calculation of updating that parameter is super cheap. It is literally just the velocity times the time step, which gives you a distance for that frame, and you're dividing that by the length of that quad or the length of the spline arc at that point, and then you're just adding that onto the parameter. So we're using that assumption that the equality increments are the same as the equal arc length increments, even if that's not true, to move these points forward. And it's incredibly cheap. And in general, yes, you will on top of this do any adjunction or lane changing decisions, but it all happens in kind of spline space and never happens in real world space. And so you can keep that very, very efficient, very cheap, very fast. But then once you do want to draw the vehicle, you've got some 3D issues, right? You've now got this point in arbitrary space, and you have a vehicle floating somewhere behind it. And you have to A, make sure it doesn't float, and B, make sure it's the right distance away in real world space from that point you've calculated, that matrix you calculated. And so our answer to that question was, well, we just line test the axles to the ground, so the vehicle stays on the ground. We place it a certain distance behind the point, and therefore it's always guaranteed to A, be behind, and also be on the ground. It looks good. Downside of that is line testing the ground is way too expensive. If you have thousands of vehicles and they're all line testing the ground every frame, that's way too expensive. So actually, to make it cheap, we just use the spline geometry itself rather than the collision mesh, and we just literally place it on the spline. And the reason why this is effective is because if you didn't do this, you would be placing the vehicle at the spline anyway. So any inaccuracies between the spline and the collision mesh are issues you'd have to deal with either way. And so this is how we ended up with quads. So the ability for us to place the vehicle on the ground really cheaply, the quads, because they had the spline index, you knew which quads to pick to check. You didn't have to check them arbitrarily. You were going down the lane. You knew which quads to check. It was just a quad check. They're guaranteed to be coplanar. As in all 4 points are guaranteed to be coplanar. And it was very, very, very cheap, basically a plane test. So that was super cool. And it meant that we could place the axles on the ground and avoid this issue. There are other advantages to quads. They perfectly tile the space, which means that if you're going between lanes, you never have a situation where your wheels, your axles, don't really know what they're above. It also had a huge win in terms of we built our junctions. Artists built the lane junctions, and so they could build the lanes for the traffic system. And they're well defined, and they're guaranteed that you can still change lanes between them well defined because quads kind of weld the spline points together, and so they can be mapped one to one. You'll always have a kind of perfect neighbor. You'll never build like two splines that have different numbers of points, and it makes it very nasty to reason about how they would change lanes between those two splines. It's a nicely well defined thing. It's easy to look at and go, that's wrong. It's easy for artists to build. It was definitely an advantage from that point of view too. It also means they control very nicely like the shape relative to the actual mesh they were building. So that had a lot of advantages. And then in terms of changing and merging lanes, once again, this kind of point ahead and point behind the vehicle. If you have a vehicle changing lanes, it basically is in both lanes simultaneously. So the vehicle that it is coming up will stop for it. So any vehicles, inverted commas, behind it in both the lanes it's in will stop for it, and it will stop for any vehicles ahead of it. So you can absolutely get the case where in this situation, the top lane vehicle, if that was stopped, could stop the vehicle that was changing lanes, and that could stop the lower right vehicle moving forwards, even though the bottom left vehicle could move ahead, because the vehicle had inserted itself in the lane and everything was going to stop for that vehicle. So it made the traffic quite polite in the sense that the traffic would always like leave room for a vehicle to come and join, but it meant we didn't have to do any collisions. It also meant that if you wanted a different policy, like you wanted to let that vehicle go, you just remove it from the lane, insert it in the lane behind it, and so on. Your policy isn't defined by this, it's defined by how you insert the vehicle in and out of the lanes and what you wanted that to be. So that's kind of the super high end, that's the end of the little presentation I had. It's just the super high end of essentially what it comes down to is this nasty problem is if you have enough spline points, you can make the assumption that these two things are the same. And yes, you will have inaccuracies, and then you make up for those inaccuracies by updating your vehicle towards the spline point and not on the spline point. You do everything in parameter space, so everything can get updated without actually having to update the vehicle at all. And you end up with something that's sufficiently diversely capable of running traffic up and down hills. They don't collide. They all work very nicely at scale.
So, firstly, thank you so much for putting together the presentation, summarizing the things we've been discussing, and like hearing you talk about it. Like, obviously, you know, pictures 1,000 words, and having someone explain the picture is a few thousand more, I would imagine. Regarding the T space versus physical distance space, if you go back to that slide where you're visualizing that. So here, or the arc, having consistent arc space versus the spacing of the actual. So here, how do you end up subdividing to get, well, I guess maybe in the end, you're just using the T spacing, right? So you're not worrying about the divisions beyond the Bezier handles that are along the curves. Is that right?
So the way this works is that because we built these traffic lanes out of quads
in the end, right?
Yeah, it meant that actually we would never build a spline like this because the curvature is way too high for a single set of spline points. Like, essentially what we're doing is saying actually every green blob actually becomes the control points along the spline.
Okay.
And therefore the error, you know what I mean? Like, it's so much denser that you never get too much curvature for any given section. And then the spline parameter, so 0 to 1 would essentially be between those green blobs, because you go 1, 2, 3, 4, 5, 6, 7, 8, 9, which means that your error is only ever as big as a small percentage of that small length. So you can basically it's a way of making it so that you're always in control of whatever error you have. And if that error is less than, like, say your error goes to be, I don't know, half a meter, as long as the spline is the spline point is a meter ahead of the front bumper of your vehicle at all times, then that half a meter error is never going to, it's never going to cause
wouldn't be a problem.
Yeah.
And that solves the problem of having to have like an even number of breakdowns. So it's all you mentioned that in the editor, you're maybe still working with spline objects, but that's just an intermediate representation to the actual geometry that's generated as you're building out those roads or authoring those intersections.
Yeah, exactly. So you could absolutely still have like big splines, like, in terms of like with control points, and do these huge curves at that level. But essentially what you're doing is actually the same thing as what you're doing with the actual visual mesh, which is you're actually making smaller shapes out of that, and then you're treating them as splines because you still want the curvature to be nice, basically.
And my last question, then I'll let others jump in here. Yeah. When you're treating the quads as splines, which is kind of like a funny concept, are you doing any interpolation to try and account for curvature within those quads, or it's just linear and the vehicle physics inherently, if they are following a point, will kind of abstract a lot of that depending on how that's implemented? I'm just curious if you're actually doing any interpolation or they're essentially treated as linear in the end.
Yeah, so actually what happened was we would so the quad is like you would actually kind of essentially take 3 quads, right? Because you end up with 4 control points with 3 quads, right? And literally your lane position was we would just essentially have a S parameter essentially between 0 and 1. Which never really got below 0.2 and never really got above 0.8. So, but we would literally just interpolate the 2 spans of the ladder of the thing, and then treat that collapse as a spline.
Gotcha. Okay.
right? So, and if you were changing lanes, same thing kind of occurs. You're now blending between two sets of lanes, and so you would end up with a curve, which means you get a nice turning curve into the lane next to you, because you're blending across multiple sections.
Got it. Yeah, I think I'm following. I'll have to think about it a little bit more, but that's helpful. But please, others on the call, you are welcome to chime in and ask follow-up questions. Anton, I know you have plenty.
Yeah, sure. One question is, I think I would like to hear more about how, as far as I understand, the quads are it's separate, right? The quads are kind of busy from the perspective of the actual vehicle, and not the param itself, right? So it's like.
So the quads. I think you got in your head because I mentioned that the quads had a link to the vehicle ahead. Yeah. But actually, to some extent, the quads have got it really is just a spline parameter that's incrementing. The whether it was a spline point or a quad, that pointer to a vehicle ahead of you is, as I mentioned, is just an optimization. And so if you move into a new quad, you're setting its next vehicle to be you. But really, it's the lane itself which is the thing where the vehicles really live. That you've got a lane and you've got a parameter, and whenever you're doing this stopping logic, none of that has anything to do with the actual quads themselves. It is literally just your parameter is increasing in value, and you calculate a parameter that you need to stop by, and that's it. And you look at the vehicle ahead of you, which you've got a pointer to directly from your vehicle. So your vehicle has a pointer to the vehicle ahead of you. You're just calculating you have to take their spline point, work out where the back of their vehicle is in parameter space, right? And therefore, and then a margin behind it just for safety, and then that's the point that you're stopping at for your parameter. So the quads don't matter in the same way as the quads are just imagine the quad was a spline, right? All you're saying is that the quad is just the integer of your spline parameter.
Yeah.
Right. It doesn't have any other meaning.
And how, what is the normal way for traffic to react for a player, let's say, that is not registered between them?
Yeah. So in terms of how we did player interactions, that varied across the games quite a bit, because what you can do offline and what you can do online are two different things. So offline, you can just do a closest vehicle check, essentially. You can say, how close is this vehicle to a point in space, which happens to be the player vehicle, and change your S parameter, essentially, so change your lane position accordingly, or stop, or those things. In online, because the traffic system itself was deterministic, we couldn't react to the player, because the player might be in different places on different clients. And so that swerving behavior was a local behavior on top of the actual traffic system. So the traffic system knew where the spline parameter was, but then you would offset relative to that based on your reaction on the local kit to that local vehicle. But that would be a behavior on top of the actual traffic system rather than built into the traffic system.
I see, but from to understand it right, that from the traffic's perspective, you can just basically register the car in front of player's car in front of the traffic's car.
So we never really did it quite like that. If you had, like, say you parked your traffic car, your player car, then yes, you would. If you would register an obstruction in the road, in the same way as any physics object you wanted to stop traffic, you'd basically put a stop line in the traffic system, and the traffic system would stop to that stop line. But once again, with online, that's not quite how it works, because you couldn't react to the player car that way, or even physics objects that way. So it kind of depended on whether you wanted it to be a local system, or whether you wanted this separation between the actual online traffic system and a local set of behaviors. And basically what would happen in the local set of behaviors is we'd have to essentially remove that vehicle from the traffic system, and replace it with a traffic vehicle that wasn't in the system that would react how you wanted to, so crash or spin out or whatever. And we would just make the vehicle that was there in the traffic system invisible and uncollidable, which means it was still in the traffic system. So it would, and that's why you often see places where traffic lights, you would see a huge gap between two vehicles, because the vehicle between them was still there, it just wasn't being drawn.
I see. I guess I wanted to ask that understand. I think I understand what how it can be done with the player's car. I wanted to ask about this param step, right? Is it always the same, or is it changes depending on speed or something? If you move, if cars move faster, then they should technically be a bit more far away from each other than if they are in close traffic or low speeds, right?
Let me just find the slide. So I'm switching which screen's on which. I think you're talking about this, right? This idea that you're just updating the parameter based on the velocity of the vehicle, right? And so the parameter update here, this velocity, you take it from the velocity of the car, but of course, how far it moves in real space has an error relative to the actual distance you want it to move, right? Say you're going 60 miles an hour, and you have a time step. Well, if you make the mathematics easy, let's see what speed is an easy time step. Either way, let's say you move a meter in a frame. In one frame, you've moved a meter. That you might have an error on that move, because the parameter is at that point actually slowing down or speeding up in its little section of the spline. But the trick here is that it doesn't if it slows down a little bit, so it's not moved as far as a meter, maybe it's moved 0.8 of a meter, I'm still moving the traffic vehicle a whole meter towards that point. So the traffic vehicle stays consistent with its real velocity, or the velocity you want it to be. And yes, it will close the distance between it and the point you're calculating. But over time, that point is going to move away from it again. Because between this very first point on the spline and the end point, that is the same distance in the end. Like, you get an error between the control points, but at the control points, there's no error. So you're always guaranteed, for any time it slows down, it'll speed up again. Like, it is guaranteed to hit the same mark. And if the density of your control points gets higher, the smaller that error gets. So as long as you've got the correct density of control points, you're always guaranteed that you'll never catch up with the parameter ahead of you. The error will never get big enough for that to be the case.
I see.
Do you end up having any scenarios where you have to fight with jitter, like the fact that you have this distance that is kind of being calculated, you're trying to find a stopping point, so you're assuming you're slowing the vehicle, but then the next frame it like jitters, it's half a meter ahead as opposed to closer or something kind of like this?
That depends on how you want to do your stopping calculation, right? Like, so we had basically we calculated an ideal velocity, it's all about time to impact, essentially. Right. So, like, if I have to be stopped by here, then how long do I have to get to that point? And you want the stopping curve to not be too linear. Right. You kind of want to stop as late as you dare. But the thing is, because we're not doing physics, in theory, you could stop the vehicle instantaneously if you needed to. But you can make that curve quite nice, where it's smoothly coming to a halt. And so it behaves very much like a real car in some senses, where once you've slowed down, speeding up again is it'll any small error, it doesn't speed up very easily. And also it doesn't slow down very much until you get very close to the stopping point. So you end up with a situation where that's blended quite well. And you don't get jitter from overshooting because you're guaranteed always to be behind it. Now, there are some cases where you've got a car changing lanes and suddenly it inserts itself into your lane and the back of it is actually behind where your stopping point is. So you suddenly, you hitting the brakes, essentially. But because it's changing lane and it's still going forwards, it will generally not clip you because it's moving forwards. And then you stay stopped until you've actually, now fully behind it. So generally, that wasn't a case where vehicles would collide with each other. And just to be clear, in Burnout, cars never, traffic cars didn't even test for collision with each other. So we just relied on this whole yeah. But you wouldn't see it.
Everybody wants that. Yeah. I see. And from what I understand from the system that you described, it is more for for mild-mannered traffic. I kind of looking more at traffic jam situation, where it's actually bad. So in these situations, big gaps where I don't know if cars are moving in parallel, basically, but one lane starts to just touch, right? And you kind of trying to, in this case, as far as I understand, the system that you propose, you still have to figure out which one is first, right? They are kind of parallel, but yeah.
Yeah, so it's entirely up to you what policy you want to put in this case, right? So, you've got a case where I've given space for a vehicle here, right now, right? But it's absolutely the case that if there was a vehicle here, then you could choose to insert this vehicle ahead or behind it. So say there was a vehicle here. If this vehicle was behind the vehicle that was here, then actually the scenario you see will happen, that the vehicle that you're inserting behind will eventually move forwards, and you're not allowed to move until you're behind their red line. So if you're way ahead of their red line, you can't move. So you just sit there in your own lane waiting for this gap to open up. But because you've inserted yourself in the other lane, the vehicle behind it won't move forward as well. And so essentially the vehicle will get out of your way and then you change lanes into the space.
Right, but it also means that kind of cars can't, like, for example, right now, we have these merging lanes, right? And essentially, from what I understand, it would basically start right from the beginning, right? We have the whole segment between two road points, one road point on one end and two road points. Sorry, not road points, but lanes on the road point.
Hold on, let me just let's see if I can. I think I have mirror open. Let me bring up that image that I had before about the changing lanes scenario, which I think is this one, right? Can you see this?
Yeah, it's coming through.
Yeah.
Okay, so in this scenario, once again, the quads aren't so important as just the fact that this is actually the same situation as we saw in the other setup, except that there's nothing to compete with when changing into the when I'm diverging. There's nothing to compete with in terms of the lane I'm coming off. If I spin this around the other way and now I'm coming in, so I'm coming in to merge. It's the same issue in terms of how I insert myself into the new lane, but there's an extra thing here. So you see the kind of bluey purple and the orangey color. This is the system going. These quads are overlapping, so you can't just when you're coming in, you can't just say, well, I'm just gonna drive until I insert myself in the other lane, because you know that your lane is actually beginning to overlap with another one. So you have to respect what's happening in that other lane because you've got the neighbor information. You can find out, and you know exactly which quads. The quads store which ones have this overlap, and also which ones have priority. So in this scenario, the orange would have priority, and so as you merge in, you would have to wait your turn to then insert yourself into the other lane to then you would park. You would get a stop line essentially before you started overlapping the actual lane that the other vehicle would have. Essentially, it's a give way sign, right? Like you end up with a stop line there, which you have to stop for until you've inserted yourself in the other lane, and then they'll have stopped, or there's space and they don't need to stop for you. So essentially, the reason why the quads are good is because you can calculate where these stop lines are or where the overlaps are, because they take up area. And actually, this isn't the worst case. The worst case is if I have a left turn across so imagine rather than this scenario, I'm actually turning across this set of lanes. Let me just change the type so I can draw a curve. So imagine I'm like turning all the way across this whole thing, and I'm coming from somewhere else. Essentially you need to know whether that's a maneuver you can pull, and the way you can do that, once again, is because the quads would cross. You can then check those lanes to see if there's time or room or space to move, and you can insert stop lines for the traffic. Once you decide you're going, you can essentially insert stop lines where the other vehicles would have to stop for you, otherwise they would collide with you. And so you can kind of automate generating a junction's stop light system, but do it by calculating whether you're where you're crossing the lanes. Now, obviously, this is only if you didn't want to just author that directly, and there are ways of doing that. But this means that you can create a junction, and for ad hoc non-traffic light junctions where you want the car to give way until there's space, this is a way of doing that, which means it could check the lane that it's going to join. Is there space? Yes. Okay, I'll insert myself, and then force any vehicle that comes in too hot, too late to wait for me, or for me to wait until there is a space.
So, a couple follow-up questions that I have. In this context, and I think that's actually very helpful the way you're describing that. So in the end, it's not that the vehicle is registering saying, hey, I'm taking up space in this quad. The quad is just used as a link to the individual lane to say where that vehicle is in placing their stop markers. And so in this case of this left turning lane, it may have to set up stoppers in like 8 different lanes.
Correct.
And then it is responsible for cleaning itself up after it's finished that maneuver, I would imagine.
Yep.
Yeah, makes sense. Okay. How do you actually represent the quads and the relationships to each other in memory? And even another thing I was thinking of is like the quads they're not physically meshes in the scene. Are they just represented in memory, or do you actually...
Yeah, so I mean, they're actually stored as rungs.
Okay.
Essentially.
Yep.
Right. So, they're in the same way that the spline itself would have point 0 the way to point N.
Yeah, so it's more like a spline data structure in a sense.
Yeah, so it's like 2 points, and then and then that way. So that's how they're actually stored.
Okay. Makes sense.
And the in terms of the proximity information. Yes, the between 2 rungs of the spline, we had data which was: is there a quad to the left of you? Is there a quad to the right of you? Am I at the wrong point? Am I joining? Is there another lane away? So in this case, in this particular case, this structure here knows that there's a neighbor to its left, and there's no neighbor to its right, and at the end of it there's also a lane, diverging lane off it. And so this particular quad, you would have those opportunities to see the emerging structure and a neighboring structure. So, but in this particular quad, there is no obstruction data because there's no. It's not orange. It's not purple. It's just clear. If you move forward one quad, this one has a neighbor, but it doesn't have a merging lane because it's the merging lane was behind it. But it does have an obstruction thing, and the obstruction data literally is another lane index and another spline, parameter index, which happens to be the quad, but it's the quad number and the spline number are the same thing.
Right. And the division here is like all across the way. It's, every 4 meters, or you have these rungs and these references at every point on every lane across the entire road system.
Yes, yeah, and each of these knows how long it is.
Yeah.
So when you're doing the velocity calculation, you store the length between the rungs, so you don't have to calculate that at runtime. Right. You just go, well, how far was it?
Yeah.
Anton?
Yeah, I have a question. I was thinking about implementing something on like that. Well, after we talked with what we have, right? And I thought about is actually stitching together quads completely necessary, because from what I think what could be possible, right? We can say that lane has some kind of fixed step of quad length, right? And then there will be some remainder at the end, right? And then we say that we can basically calculate from an offset that we have the same offset on the nearby lane, what I did by basically making using the same ratio, right? If we have ratio, then we could basically transfer, like if car is moving, then we could transfer from one lane to another without, and the quads would be either always the same length and the remainder at the end, or we could make it a bit flexible, and that, but they could still be like in, well, it would be all the same, right? So we wouldn't need to kind of make quads longer or shorter on the spline. Do you think it would make sense?
So the question I've got to you before we get into that detail is where do you want the spline to represent on the vehicle? Right? So in this particular scenario, we had the spline point being something that was the stop point, right? And that let us run everything at, in T, and we didn't have to, and so, but it does mean that if you've got your spline point at the stop point, at some level, you have to try and actually put the vehicle on the road or on the spline. Now, if you're running physics for all your vehicles, sure, you don't care, you're just running physics and you're fine. But if you want to do what we were doing, which was only run physics for a very tiny minority of vehicles, then you still have to have a way of putting the vehicle on the spline. One way is to make the actual spline point the model center, the model position of your vehicle, place it that way.
Yeah.
But then you still have the issue of, well, how big is this vehicle front and back relative in your spline positions? And so you have a problem that because the vehicle takes up physical space, one spline point will never accurately represent that. And so the reason why we ended up with the quads was because rather than trying to be like, and PlayStation 2 didn't have much in the way of performance. We couldn't do like lots of accurate spline positionings, and actually we couldn't even do even with this, the reason why this is so powerful was because we could just stay in parameter space and actually not calculate anything unless we absolutely needed to. But that meant that we had to embrace that inaccuracy, which meant that we had to have a different way of placing the vehicle, which meant the quads made sense. So quads had this double meaning, right? They had the meaning of the physical space which the vehicle could represent being in, as well as the thing. And also they guaranteed that we didn't get situations where an artist or someone had created a situation where there were different numbers of spline points in parallel lanes that would cause all sorts of nasty situations about how neighbors worked with each other and what the shape of those things were. You absolutely could have a spline and go, it's just a spline, and frankly, we don't really need to deal with quads. But it actually just made everything easier, especially for artists, when we were asking them to actually like draw lanes, for them to weld them together so they guaranteed that they just worked, rather than having a system where they were just trying to kind of match up splines and hoping that the system would do all the work to try and deal with it. So it kind of it was kind of an optimization in a couple of ways. One, it was easier to reason about, and it meant that we could do this trick of making the spline point be something you were driving towards rather than being the actual representation of the vehicle itself. Once again, you absolutely could do it without quads. And actually, just to be super clear, at runtime, we were just collapsing everything into splines. Like with the road position, like we took the road position and we just that's how we moved the spline along for the thing. So I mean, it absolutely works that way. But it just meant that we had that extra little bit of information about the width, like where the width of that spline was really connecting up with the width of the spline of the neighboring spline, and making sure that they stayed in sync with each other when things were happening. So it was a constraint on authorship, but it did actually simplify the runtime code a lot because you didn't have to do anything clever. You literally knew that if you had a neighbor, then it was perfectly, it was a perfect neighbor. You didn't have to do anything clever to work it out. You didn't have to do anything clever with, like if you had bank turns or whatever, it all just worked because you had that extra piece of information.
Mm-hmm.
But once again, like there's different layers to this, right? So, the quads, like the authorship story, how you build the spline and what kind of lanes you get out of it, and how you connect them for junctions. How do you do things like just give way junctions rather than having to force everything to stop with invisible traffic lights and all those things? Like there's a number of kind of authorship questions. And then there's the runtime. How do you do this incredibly efficiently? And they're kind of two separate pieces. What I would say is that, like, if you can run the traffic system in your parameter space and not in real world space, you can do hundreds of thousands of traffic. You could do a SimCity full simulation, because literally all you're doing is updating a bunch of parameters, and you can go to that kind of scale. And it could scale all the way down to just following physics and doing it that way. If you go heavyweight on the update and you have to do everything in real world space, that will limit how much you can run in the system itself. Obviously, you get more behavior potentially, but that's just one of the trade-offs.
Yeah, no, it definitely sounds very compelling, and especially the multiple birds for one stone, as you say, with like the placement of the vehicles, the tilting of the vehicles to the planes, all makes a lot of sense.
Yeah, and it's artist friendly as well, which is the other really big win. If you've got a really nasty, complicated junction that you can't auto-generate, for them to be able to lay out what the traffic should do in it was at least intuitive to them in terms of how they should author it. So that was also just a huge win from that point of view.
Yes, in those scenarios, they're laying out the actual lanes, that visualizing the widths and how they kind of do or don't snap together in certain scenarios, and then they're creating the actual display geometry. They're modeling that around once they have those lanes more or less figured out, I imagine.
Yeah, and also just to be clear that in the case where you had a crossing lane, something crossing that wasn't connected, they were guaranteed that you wouldn't weirdly change lanes just because they were crossing. They were kind of encoding the adjacency information by welding the quads. And if they weren't welded, then they weren't connected.
And so that welding.
Yeah, but
Anton, go ahead. Maybe the same question.
Yeah, by the way, I just wanted to ask about, when I was thinking about this system, I was also kind of not this one, but what I had with it was fine. I also was thinking about kind of like communication subsystem between multiple agents, right? So, for example, if somebody is approaching the intersection and already can't stop before it gets to the point where lines intersect, they could put something in there to say that please don't come closer.
Yeah, so if you've got so on top of this system we had a traffic light system. So the traffic lights would have a stop line, right? So they would insert, like, the red marker here. Imagine that wasn't a blob; it was a line. The traffic system would be in control of whether that thing was on or off or whatever. And once again, it would have information about the vehicle behind it, i.e., what was the next vehicle coming up to it. If you wanted to have a thing where that vehicle also has a pointer to the stopping object because it's the next thing in its lane, it's not a vehicle, but it's the thing you're stopping for, then it has a pointer to your control object, which you can say, hey, I'm coming in too hot, let me through, or there's always a communication because you have a direct connection to that object, essentially. That's kind of one of the advantages of this system. The one thing to note, I would say, is this ran. The reason why I'm saying pointer is because these were raw pointers, because system was just assigning vehicles to the array, and therefore their position in memory was consistent and permanent, and it wasn't a variable length array, and it wasn't one of those things that kind of moved things around in memory. It was absolutely, there was a fixed number, and we assigned you an index essentially, and that was it. And so we had very stable behavior that way. Obviously, in modern systems, you've got to make some choices about how you do that. With C++, for example, in the vehicle game I'm making, I use PLF colony, rather than vector, and it has a very nice behavior where it's like it works like vector, except that it only ever like adds a block rather than the block you already have. It won't copy to a new block of a new size. If you need more memory, it'll just assign you another block, and then it'll assign you another block. And it's incredibly efficient about walking the multiple blocks. So you get the performance of a vector, but you have pointer stability, and you have a bunch of nice things about never having to copy your data around, which is really good. So that's a really nice structure for games, which is kind of similar to this in terms of like being a fixed array, but is variable length, which is nice.
Yeah. Also really says the devil's ends up being in the details of how these objects are managed in memory and GDScript and so forth, and how we structure them. But
yeah, I mean, obviously the most efficient version of this would be to have a C++ module that was sitting underneath
doing all of that,
doing all that stuff, and then the GDScript is really just the hooks into that system rather than the system itself.
Yeah.
I don't really know how efficient GDScript is relative to C++ or even C# if you're using C# scripting. I'm guessing that a lot of people don't ship C# like plugins because not everyone's using C#. So it's
exactly. Yeah, GD extensions though, there is a good hook for that in the engine. It's a way just to plug into the engine's APIs and you just have your own private logic there. In terms of the performance, if you put the range of C++, handcrafting to Python, it's much closer to C++. Python's not a great reference, but for the flexibility, it's it can do some pretty good optimization, especially where you're pretty strict about your typing. But you have to be intentional where you're doing your optimization for it to be a benefit to go into C++. It may not necessarily be better in some scenarios.
Yeah, and just to be clear, in the kind of hundreds of thousands of traffic sense, doing a data-oriented design, i.e. that the parameter literally has just enough data to be updated, and you have a huge array of them, and so you just blast through them in one pass, is like, so literally we had a vehicle param structure that didn't have a matrix. Like it was literally just enough to update the param in its line, and then we had a vehicle kind of matrix class that went along, and if it was instantiated, it would take its own param and generate where the vehicle was, and then on top of that, there was actually a traffic vehicle that had graphics and and all those things. And so because the traffic vehicle that vehicle matrix could be ripped out for a physics vehicle underneath, so it could switch dynamically between a physics vehicle and like this vehicle matrix, which sat on top of the vehicle param. And it was incredibly cache efficient. Like I think throughout our entire traffic system update, we because PlayStation 2, for example, has this scratch pad, we had very, very, very few cache misses because we were DMAing that data to the scratch pad. So virtually all the data was essentially kind of prefetched in cache. So there was actually, if you actually looked at the performance like grab of that data, it was incredibly fast because you were never hitting memory. So like you can do all sorts of crazy optimization with this kind of setup, because you're dealing with very small amounts of data and a lot of it, but you can rip through it very, very efficiently. So that's why it scales to the kind of SimCity potential situations you might want to support. But yeah, I mean, ultimately, we built this a certain way because this is the way that we built it. On Burnout Paradise, which was open world, for network purposes, we actually had traffic regions,
right,
which were turned off and on, and they were synchronized to be turned off and on at the same time. So if you had a huge open world and everyone was in one location, like you only had traffic in your region. But if one of the cars was over on the other side of the map, that traffic region was also on. And they would, so even if you weren't anywhere near them, you'd still be doing the parameter updates. But of course, you wouldn't be doing anything other than just doing the parameter updates for over there. We could have probably done the whole world without the region system, to be honest, given how powerful machines are, but it seemed like a reasonable optimization just to kind of segment it into cells and do it that way. So you can even do like there's layers of hierarchy you can add on top of this as well if you wanted to. But yeah, so basically the big bit of feedback I would say is, if you want this to scale, being able to do all your lane changing and stopping and those things in parameter space is a huge win. There are some options then about how you get out of parameter space back into vehicle matrix space. The quads were one way, but of course you could implicitly have you could imply a patch, like use these lanes as a Bezier patch and kind of treat it that way as well. Mm-hmm. Like if you had the right connectivity information, then you wouldn't have quads. You'd have this surface that you could do, and that's viable. Once again, it was just because we were limited in performance and limited in memory and all those things. Modern processors are much better than those old machines were against this stuff. So you've got lots of options. I just wanted to kind of communicate, like, that the big win you're going to have is if you can make the assumption that the arc lengths and the equal T increments are actually the same because you've got a density of control points, then you can do everything in parameter space and you'll save yourself a lot of performance. And yeah, whether you end up with quads in the bottom or not, it is a nice thing to have, especially for placing vehicles and those things. But once again, you could do it with a spline patch or whatever. Yeah, so the choice is yours a little bit.
Great, really appreciate that, and I want to be respectful of your time as well. It's a full hour here. Any last questions from either Liam or Anton?
I think maybe I would. Yeah, sorry.
I was going to say I've got nothing to add. I've been kind of quiet the whole time. I've mainly been picking up the pathfinding stuff because that's what I was looking at with the Road Generator, and I've got no complaints about any of this really. Like I can see how what I've done already would translate into this quite nicely. So all good.
Great.
I have maybe one small question about like changing lanes for. What do you do for changing, basically how the param changes from one lane to another to create a new...
Yeah, so you've got a couple of options. It kind of depends on how fast you want the lane change to occur and how spaced your quads are. So if you want the lane changing to occur about the size of your quads, then literally you could just like switch out the spline point, the control points to blend in using the new control points. Just like you form a curve that way. The other thing you can do, which is also completely viable, if you want it to change lanes slower than that, is literally calculate both splines and then interpolate between them slowly. So you just you've got both, because you're once again you're guaranteed that these quads are like the nice thing about this is because you're guaranteed the number of conditions is the same between the two. You can generate two splines and then just like, you know, linearly interpolate between them, and that linear interpolation will also help you like know which quads to do your axle checks in and those things. So that's one of the things about this is you end up with something that's actually really easy to implement, which is just you linearly interpolate between the two curves.
Mm-hmm. I see.
And then in terms of, I guess, the other like details, like we've been contemplating how to represent the obstacles, like whether that's a resource that has a reference to an offset. I mean, in this case, the stoppers themselves, it's an array, you could say, of positions.
The stoppers they're just another thing in the linked list.
Right.
Right.
Okay.
They have
So it can go rung, stopper, rung in that sense?
No. So the rungs aren't in rungs aren't in the list.
Right. That's just the
right. Yeah. So they're an acceleration structure to get you into the list.
Right.
But the rungs aren't in the list themselves. No vehicle will point to a rung. No.
Okay. Yeah. Okay.
The rungs aren't objects in that sense. So if you want to put a stopping point in, you do the insertion like you do for the traffic vehicle merging. So you go, I have an object. I'm going to, take the next pointer of the vehicle behind it and point it at me, and I'm going to, insert myself in this linked list.
Right.
And then the stopping, the previous list stops. The only thing with the rungs is that we once again, it's an acceleration structure. They can point to the vehicle ahead of them, and that gets updated when you do the parameter update. And obviously, if you know the you know your parameter, you also know which rung you're in, because that's just the hint. Yep. The floor of your parameter is the rung you're in. So what you can do is say if I go to if I'm merging with a lane, and I look at so I go to let's do it in the clearest example I've got here. Yeah, back in mirror. Okay, if I'm going to change lanes here, this car is going to change lanes. I know my neighboring lane. I can then use that acceleration structure to look up whatever car is ahead of me, right, in that lane. And then I can use the linked list of that vehicle to go back to the vehicles behind this point.
Right, and then see what space you have and where you need to insert
and see what space I have and so on. Yeah. And then I can also look at that vehicle parameter and know which quad it's in if I needed to, although generally you don't, because what you really care about is the distance, not the actual quad index.
Yeah, that makes a lot of sense. We were contemplating, are we going to have like an instance shadow of our like road agent to be in two places, which would be a lot of overhead, a lot of unnecessary memory, but like truly treating it as a linked list.
Yeah, it's a doubly linked list, so you
go both directions.
In both directions, so you can find any vehicle along the list and find any vehicle behind you, and that's why you can, like at a junction, you can, if you're waiting for the traffic to go by, if you know the vehicle ahead of you, because you trivially can find that, you can then go as far back in the setup as you want, and then you can insert yourself into that lane. So one thing you could do is go, imagine I've got an acceleration speed. Right. I want, there's a time taken for me to speed up on a highway.
Sure. You're gauging where you want to be. Yeah.
I can go back and find a point to insert myself, and that vehicle will slow down for me as it gets close enough, because I'm already ahead of it in its lane.
And it's updating its reference as you're going along to kind of join up to the point where you actually merge into that lane, right?
You don't have to update your reference, because not the
stopping point that you're tracking against, right?
Well, you have a fixed stopping point. So they if you're now ahead of them, then they they can go until they get to you to slow down and stop.
Okay.
Now you do get some interesting scenarios there where you have to be a little bit careful, where if you go far enough back, if the vehicle ahead of them is actually behind you too, and that vehicle stops, then you want them to stop for the vehicle actually genuinely ahead of them. So you have to be a little bit careful about. But it does mean you can find an insertion point, and the way you generally do that is you remember where you insert, and actually you only insert once the car ahead of it is ahead of you, so that so you're not actually inserting until you just in time you need to.
Okay.
But you know where you're going to insert, and in theory you could speed up to know you're going to insert in that place. And because in our case the vehicles aren't physical, they can stop instantaneously if they need to. You just never see it because that never really happens. It's a bit like cars can actually go through each other and merge. Like they don't collide. But once again, 99.999% of the that would never happen, so you just don't see it. So you have to deal with it.
Yeah, nice. Awesome. Well, thank you so much. Really appreciate it. And as well as your contributions, as you're thinking about how you're using the road generator, looking forward to having you in the community. And
yeah.
So,
and Anton, if you have more questions, feel free to ping me. Like it's fine. Like it's no big deal.
Yeah, thanks. I think I will try to implement something like that. Change my branch to do that. I think I will ask you to review it. And so.
Yeah, at some
I'd be
point...
happy to, and I can also send you this deck if it's useful, Anton, as well. I can send you the slides.
Okay, yeah, thank you.
Yeah, I was gonna, at some point, like as you get to that Anton, it's probably good if we want to like huddle or sync, it could be asynchronous or live, about even just like the structures that we would be like contemplating putting in place to see how they marry up and how that can relate back to the agents and all those good things. So as you're welcome to continue on, like experiment for sure as you start to think about those things, but at a certain point it probably will make sense for us to sync some more.
Yeah. I think I will. I think I will try first without like actually creating quads because first of all, for me it's not like that relevant. I would say that I can go with splines, but I think they are needed, like stitching them, everything like that. But I think I would change my stuff to actually do it in a linked list and with like buckets of quads, like buckets of agents, right? To move them through the lane. I will split it somehow, but we can always discuss how it has to be done when it's going to be merged.
And just to be clear, Anton, that's what I would have recommended you do, which is don't worry about the quads to begin with. Just have these lanes where traffic has next and previous, and you can make good decisions about how to merge or diverge into those lanes.
Yeah.
Because to be frank, even if the traffic was floating behind the point and it wasn't actually on the road correctly, for now you don't really care, right? Like it's fine.
Yeah.
And then, only when you get to that point where you're talking about having precision about where you want these things to go, we talk about what the best way of achieving that is. So yeah, I definitely think, especially given the charts you were showing in the doc, the thread that we were in on GitHub, the ability to like correctly like have a traffic jam where things are diverging, staying good distances behind each other and not colliding and not having all that in really good place, and for it to be to be able to update it effectively. I think that would be the biggest win you can start off with.
Yeah.
Adding the overlap, like the more complicated cases could come later.
Mm-hmm. Yeah, that's my thought as well. I'll keep you posted on my progress then.
Yeah,
Perfect.
I'm excited. I think it's going to be interesting. I mean, I think as I was saying before, it's kind of funny that you see all these systems for Unreal or whatever, and it would make me chuckle if Godot actually had the best one. So
That's the goal. Yes, here we go. Let's make it happen.
So yeah, it's good to do these things.